Mm, Hello, everyone. I'm Mingtao Xia, a third-year PhD student from the Math department, and it's very nice to give a talk in this QC Bio retreat. Today, the topic of my presentation is mathematical models for device testing and vaccination strategies. For the ongoing COVID-19 pandemic, testing and vaccination play a very important role in containing the spreading of the disease. Testing can help us identify and quarantine infected persons with smaller costs because we only need to quarantine those who are tested positive instead of quarantining everyone. And vaccines can help us protect the most vulnerable people from being infected. Combining them together, we can contain the spreading of the disease. Actually, we have spent quite a lot on testing. $1.5 billion program in the United States was initiated for providing 6 million tests per day, but we didn't reach the goal. In order to improve the efficiency of testing, we had to do pool or group testing, which means that we collect samples from different persons together and test them at once. The other way to go, which I'm going to introduce today, is to test based on social activity, which means that we only test those who are presumed to be at a higher risk. In our recent work, an agent-based model is proposed, which takes into account the contact time. So we can see that at each step, the risk is measured by this green bar, and those persons with a high risk are selected and receive tests. So this is an agent-based model. It can be applied to a relatively small number of population, and when the interpersonal contact time data is available. But what if the persons in a population become very large? Then we may need some mean-field models. Mean-field models are described for a very large population and can efficiently compute optimal control strategies. Also, the strategies may be more interpretable. However, when we come from the agent-based model to this mean-field model, we must give up individual resolution and also some possible higher order degree correlations. We consider two network models. The first one is a Barabazi-Albert network, in which the degree distribution decays exponentially with the degree k. The second one is a stochastic Blow model. So this model is like we connect several neighborhoods together, and it looks like this. And the most nodes have a degree that is close to the mean degree. So here is the effective degree testing model we have constructed. Based on the standard SIR model, we further divide the infected compartment into two sub-compartments, the untested group and the tested group. Also, for each compartment, different peoples are characterized by different degrees L. The untested group can be converted to the tested group by testing, and the testing rate is the F of L divided by P of L, the budget divided by the fraction of population in that group. Typically, for the tested group, their infectious rate is much smaller than the untested group because we can quarantine those who are tested positive. Also, their recovery rate can be different. So our goal is to reduce infections under a limited resource constraint. For instance, if the daily number of tests is limited, how do we best allocate the testing budget for different subgroups so that the total infections can be minimized? In order to achieve this goal, we define this target function, which is the total infections in the time interval from 0 to capital T multiplied by a factor rho of T. Here rho is a discount factor, which penalizes later infections less than earlier infections, because we know that earlier infections may play a more important role because since we are not well prepared for the disease. In In order to minimize this target function, we construct this Hamiltonian and minimize this Hamiltonian for every t. We can see that the risk for each subgroup characterized by the different degrees is clearly seen by this red term, and the smaller this term is, the higher the risk for that subgroup is. So our strategy is to maximize the testing budget for those groups with a smaller this red term. Here are some results for the two networks. We can see that for both networks, the strategy is to test those with a higher degree from the beginning, but as time goes by, when those persons are almost infected, we then turn to test those with a smaller degree. Also, for the Barbasi-Albert network, the effect of optimal testing strategy is more apparent than the stochastic block, because in this network, very few nodes have very large degrees, and as long as we contain those nodes with a large degree, we can successfully contain the disease, because most nodes have very small degrees and they could avoid infections. Also, vaccination plays a very important role in protecting those susceptible persons from being infected. We can construct this effective degree vaccination model from the SIR model. Here, we assume that one susceptible person after receiving one dose of vaccine can become fully immune to the disease and turn to this recovered group. Also, the question is, given the constraint on daily vaccine doses, how do we determine the allocation of vaccine resources for different groups with different degrees to minimize infections? So here are the results for the two networks. We can see the strategy is also to vaccinate those with a larger degree from the beginning, and as time goes by, we then turn to vaccinate with those with smaller degrees. So it's similar to what the strategy that we took in the real world. We first vaccinate those critical workers or medical workers who are more likely to get into contact with more people, and then turn to vaccinate those turn to vaccinate everyone. And actually, for the Barbasi-Albert network, it is hopeful that we can fully contain the spreading of the disease under the optimal vaccination strategy. For the stochastic block model, although we cannot fully contain the spreading of the disease, the effect of optimal vaccination strategy can much reduce the total infections. As a comparison, we also implement reinforcement learning strategy. So here we compare the Pontryagin maximum principle approach we used before with the reinforcement learning strategy. Actually, since the Pontryagin maximum principle always gives the optimal solution, the RL approach cannot perform better than Pontryagin approach. But here, we found that we could use the Pontryagin approach to pre-select the possible optimal actions for RL training and reduce the uncountable action space to a finite action space and improve the efficiency of training. So this could be helpful in other problems where we cannot directly apply the Pontryagin approach to solve the optimization problem. And our future work, we plan to consider contact time distribution and dynamical networks in which the structure of the network may change over time, and then implement real data and use more realistic loss functions to take into account more factors like economic impact. Finally, we are considering simultaneous testing and vaccination like what is happening in the real world. Thank you.